Okay, now let's get started. Introduction to Neural Prediction for Word Propagation. In this chapter, a simple network making a prediction. Okay, that's the list of the contents, but we don't have to read it by our own. I try not to get involved in the business of prediction. It's a quick way to look like an idiot. Why he would say that? It's basically because if he was involved in that prediction, after that thing happened, people would know whether he's smart or not because the truth will tell them that. Step 1. Predict. This chapter is about prediction. In the previous chapter, you learned about the paradigm. Predict, compare, learn. In this chapter, we will dive deep into the first step, predict. You may remember that the predict step looks a lot like this. By giving the data, the machine give you the prediction. In this chapter, you'll learn more about what these three different parts of a neural network prediction look like under the hood. Let's start with the first one, the data. In your first neural network, you're going to predict one data point at a time, like this. By giving it a number of times, the machine output the prediction. Later, you'll find that the number of data points you process at a time has a significant impact on what a network looks like. You might be wondering, how do I choose how many data points to propagate at a time? The answer is based on whether you think the neural network can be accurate with the data you give it. For example, if I'm trying to predict whether there's a cat in a photo, I definitely need to show my network the whole pixels of that image. Why? Because if I send you only one pixel of an image, could you identify whether it's a car or dog? No, you can't. Me either. That's a general rule for that. Always present enough information to the network, where the enough information is defined as how much a human might need to make the same prediction. Let's skip over the network for now. As it turns out, you can create a network only after you understand the shape of the input and output datasets. For now, shape means number of columns or number of data points you are processing at once. Let's start with a single prediction of the likelihood that the baseball team will win. Now that you know you want to take one input data point and output one prediction, you can create a neural network because you have only one input data point and one output data point. You are going to build a network with a single norm mapping from the input point to the output. Abstractly, these lambs are actually called weights, and I'll refer to them as such from here on out. So, without further ado, here's your first neural network with a single weight mapping from the input terms to the output when. Here's your input data, here's your output. As you can see, with one weight, this network takes in one data point at a time and outputs a single prediction. A simple neural network making a prediction. Let's start with the simplest neural network possible. Okay, well, from now on, I'll start to code. The weight equal to 0.1. We define a function with the length of neural network by giving its input and we have to give it two parameters, the input and the weight. The prediction will be equal to input times the weight. And we have to return that prediction. Done. That was an empty network. It's just a function. At the step 2, we have to insert in one input data point. So we have to define our data this time. The number of times would be equal to 8.5, 9.5, 10, 9. The input would be equal to the first element of a number of times. The prediction would be equal to the neural network. Yes, by giving it the input, you'll get the output. And we have to print out the prediction. Okay, it is a neural network missing one required positional argument, the weights. Sure, I have to give it the weights. Good. The prediction is calculated by the input times the weight. It will return you the prediction. Deposition the prediction. Right, it's just a number. What is a neural network? Here is your first neural network. To start a neural network, open a Jupyter notebook and run this code. Just have to define the weight, the neural network. It's a function. And all such a thing. You just made your first neural network and use it to predict. Congratulations! The last line prints the prediction, PRED. It should be 0.85. So what is a neural network? For now, it's one or more weights that you can multiply by the input data to make a prediction. Okay, that's simple. I didn't know that before. You know, before I read this book, I only know how to use some frameworks like TensorFlow or Keras. I don't know the details behind those fancy frameworks. But by reading this book, you'll generally understand what's going on behind those frameworks. So what is input data? It's a number that you recorded in the real world somewhere. It's usually something that is easily knowable, like today's temperature, a baseball player's betting average, or yesterday's stock price. What is a prediction? A prediction is what the neural network tells you, given the input data, such as given the temperature, it is 0% likely that people will wear sweatshirts today, or giving a baseball player's betting average, he is 13% likely to hit a home run, or giving the yesterday's stock price, today's stock price will be 101.52. Is this prediction always right? No. Sometimes a neural network will make mistakes, but it can learn from them. For example, if it predicts too high, it will adjust its weight to predict lower next time, and vice versa. How does the network learn? Trial and error. First, it tries to make a prediction, Then it says whether the prediction was too high or too low. Finally, it changes the weight up or down to predict more accurately the next time it sees the same input. It's just like human, right? What does this neural network do? It multiplies the input by a weight. It scales the input by a certain amount. In the previous section, you made your first prediction with a neural network. A neural network, in its simplest form, uses the power of multiplication. It takes an input data point, in this case 8.5, and multiplies it by the weight. If the weight is 2, then the neural network will double the input. If the weight is 0.01, then the network will divide the input by 100. As you can see, some weight values make the input bigger, and other values make it smaller. Okay, that makes sense. If the weights change, the output value change. An empty network. This is the same network we have seen before. The interface for a neural network is simple. It accepts an input variable as information and a weight variable as knowledge, and outputs a prediction. Okay, that's a fresh new definition for me. I don't know that before. Every neural network you'll ever see works in this way. It uses the knowledge in the weights to interpret the information in the input data. Later, neural networks will accept the larger, more complicated input and weight values. But this same underlying premise will always ring true. In this picture, in this case, the information is the average number of terms. 8.5 is indeed the average information of the terms on a baseball team before the game. Notice several things. First, the neural network does not have access to any information except one instance. If, after this prediction, you were to feed in number of terms element 2, the network wouldn't remember the prediction it made in the last term step or in the last term. A network knows only what you feed it as input. It forgets everything else. Later, you'll learn how to give a neural network a short-term memory by feeding in multiple inputs at once. Multiplying input by weight. I just said that before. Another way to think about a neural network's weight value is as a measure of sensitivity between the input of the network and its prediction. If the weight is very high, then even the thinest input can create a really large prediction. If the weight is very small, then even large inputs will make small predictions. This sensitivity is akin to volume. Turning up the weight amplifies the prediction valued relative to the input. Weight is a value lump. Okay. Deep-setting the prediction. In this case, in this picture, what the neural network is really doing is applying a value lump to the number of terms variable. In theory, this value lump can tell you the likelihood that the term will win based on the average number of terms per player on the team. This may or may not work. Truthfully, if the team members had an average of 0 terms, they would probably play terribly. But baseball is much more complex than this. In the next section, you'll present multiple pieces of information at the same time, so the neural network can make more informed decisions. Note that neural networks don't predict just positive numbers. They can also predict negative numbers, and even take negative numbers as input. Perhaps you want to predict the probability that people will wear coats today. If the temperature is negative 10 degrees, then a negative weight will predict a high probability that people will wear their coats. Making a prediction with multiple inputs. Neural networks can combine intelligence from multiple data points. The previous neural network was able to take one data point as input and make one prediction based on that data point. Perhaps you've been wondering, is the average number of Toms really a good predictor all by itself? If so, you are onto something. What if you could give the network more information at once than just the average number of Toms per player? In this case, the network should, in theory, be able to make more accurate predictions. Well, as it turns out, a network can accept multiple input data points at a time. Take a look at the next prediction. This is a network with multiple inputs. Here you give the multiple inputs, the terms, the win-loss, the fans. You give it then 3 different type of information at once. The weights become something like this. The neural network function will still take 2 parameters, the input and the weights. But we use a different way to get the output. We use a function which called WSUM. The second picture, inserting one input data point, one row of data. This dataset is the current status at the beginning of each game for the first 4 games in a session. Terms, current average number of terms per player. Varic, current games won, %. Fans, fan count in millions. Okay, this is how the input was generated. So here you got 3 last, and all input was generated from the 3 last. We just want to take the first element of the 3 last, then feed it to our neural network. Okay, did you notice that the weights are different? The weights are also three elements. So it has 3 elements. The weights has 3 elements, and the input has 3 elements. It's corresponding, right? It has the same length. And here's how he defined the WSUM function. It will first assume the length of input data equal to the length of weights. Then the output at first, it is equal to 0. For every element in the 2 lasts, we get the output by just add the previous multiplication of the input times the weight. Okay, it's just the sum of output. As you can see, 85 times 0.1, you get 0.85, and 65 times 0.2, you get 0.13. Then you add those outputs together, you get the sum of those outputs. You can see it from this picture. It's very clear for how it works. Then we combine those things together. Multiple inputs. What does this neural network do? It multiplies 3 inputs by 3 num weights and sums them. This is a weighted sum. At the end of the previous section, you came to realize the limiting factor of your simple network. It was only a value num on one data point. In the example, that data point was a baseball team's average number of toms per player. You learned that in order to make accurate predictions, you need to build neural networks that can combine multiple inputs at the same time. Fortunately, neural networks are perfectly capable of doing things like that. Okay, this is the same picture we have seen before. This new neural network can accept multiple inputs at a time per prediction. This allows the network to combine various forms of information to make better informed decisions. But the fundamental mechanism for using weights hasn't changed. You still take each input and run it through its own value norm. In other words, you multiply each input by its own weight. The new property here is that because you have multiple inputs, you have to sum their respective predictions. Thus, you multiply each input by its respective weight and then sum all the local predictions together. This is called a weighted sum of the input, or a weighted sum for short. Some also refer to the weighted sum as a dot product, as you'll see later. A relevant reminder: the interface for the neural network is simple. It accepts an input variable as information and a weights variable as nullity, and it outputs a prediction. Okay, what does that mean? A relevant reminder. Oh, it's a reminder. So this is an important sentence for you to understand. Okay, this is the same picture we have seen before. This new need to process multiple inputs at a time justifies the use of a new tool. It's called a vector. And if you have been following along in your chapter notebook, you've already been using it. A vector is nothing other than a list of numbers. Okay, it's just a list. Remember, a vector is nothing but a list. In the example, input is a vector, and weights is also a vector. Can you spot any more vectors in the previous code? Of course we can. Anything that has a less symbol, it is a vector. As it turns out, vectors are incredibly useful whenever you want to perform operations involving groups of numbers. In this case, you are performing a weighted sum between two vectors, a dot product. You are taking two vectors of equal length, input and the weights, multiplying each number based on its position. The first position in input is multiplied by the first position in weights and so on, and then summing the resulting output. Anytime you perform a mathematical operation between two vectors of equal length, where you pair up values according to their position in the vector, it's called an element-wise operation. That's element-wise addition sums two vectors, and element-wise multiplication multiplies two vectors. Okay, this sentence is quite complicated. It's one sentence, and also it's almost a parameter. Okay, it is said when you iterate elements from a list, what you are doing is called the element-wise operation. It's quite ridiculous. Why does he just use the recursive? No, why didn't they just use iterate? Maybe he just want to make it as simple as possible. Challenge vector math. Being able to manipulate the vectors is a cornerstone technique for deep learning. Say if you can write functions that perform the following operations: element element-wise multiplication, element-wise addition, vector sum, vector average. Then see if you can use two of these methods to perform a dot product. Yeah, we can do that. Shouldn't be too difficult. Okay, that's it. If you want to do a element-wise multiplication, all you have to do is do something like this. First, you check if the two last has an equal length. Then, you just iterate the elements from that last, and you get its multiplication value. Then you add it to the output variable here. Then you output it. It's quite simple. And if you want to do some addition stuff, you can just change the symbol to plus. That will do it. It's quite simple. Here it is the same as we did, but it just used a different method to assure it has the same length of elements. It uses a keyword assert. It's the same picture there. The intuition behind how and why a dot product weighted sum works is easily one of the most important parts of truly understanding how neural networks make predictions. Loosely stated, a dot product gives you a notion of similarity between two vectors. I don't understand that. The highest weighted sum CC here is equal to 2. It's between vectors that are exactly identical. In contrast, because A and B have no overlapping weight, their dot product is 0. Perhaps the most interesting weighted sum is between C and E. Because E has a negative weight, this negative weight cancelled out the positive similarity between them. But a dot product between E and it itself would yield the number 2. Despite the negative weight, double negative turns positive. Let's become familiar with the various properties of the dot product operation. Oh, I didn't expect the dot operation is something just as simple as this function. Oh, neat shit. I used to know how to how to do the dot product, in mathematics. I used to learn that at university. I didn't expect it's just something that's as simple as this function. Oh, sometimes you can equal the properties of the dot product to a logic AND. Consider A and B like this. A equal to this, B equal to this. If you ask whether both A element 1 and B element 1 have value, the answer is no. If you ask whether both A element 2 and B element 2 have value, the answer is again no. Because this is always true for all 4 values, the final score equals 0. Each value fills the logic AND. Yeah, it cannot be both 1 in this A-B nest. And consider B and C, however, have one clone that shares value, a clone string. It passes the logic AND because the third element of B and the third element of C have weight. This clone and always this clone causes the score to raise to 1. 1 times 1 equal to 1. And consider the C and D. Fortunately, neural networks are also able to model partial ANDing. In this case, C and D share the same clone as B and C, but because D has only 0.5 weight there, the final score is only 0.5. We exploit this property when modeling probabilities in neural networks. What does that mean? I don't know. Oh, I get it. 0.5. We can also get that value less than 1, between 0 and 1. In this analogy, negative weights turn to imply a logic NOT operator, given that any positive weight paired with a negative weight will cause the score to go down. Yeah. Furthermore, if both vectors have negative weights, such as weight sum of E and E, then the neural network will perform a double negative and add a weight instant. Additionally, some might say it's an OR after the AND, because if any of the rows show weight, the score is affected. Thus, for weight sum of A and B, where is A and B? Okay, here it is, A and B. If A and B or A and B and so on, then the W sum AB returns a positive score. Okay, that's too complex for us to understand. Amusingly, this gives us a kind of crude language for reading weights. Let's read a few examples, shall we? This assumes you are performing weight sum input and weights, and then to this if statements if an abstract then give high score. What? The weights equal to 1, 0, 1. You can translate this sentence to if input 0 or input 2. Okay, let's say what he was thinking about. It is said the first element should be, I don't know, this output will only depend on the first element and the last element, which is indexed 0 and indexed 2. And this one, the output will only depend on the last one, which is the input indexed 2 of input. And also this output will depend on the first element of the input and the last element of input. And also if you want to get a positive output, you should make sure that the last element of input be negative 2. Notice in the last row of weights 0 equal to 0.5 means the corresponding input 0 would have to be larger to compensate for the smaller weighting. And as I mentioned, this is a very crude approximate language, but I find it immensely useful when trying to picture in my head what's going on under the hood. This will help you significantly in the future, especially when putting networks together in increasingly complex ways. Given these intuitions, what does this mean when a neural network makes a prediction? Roughly speaking, it means the network gives a high score of the inputs based on how similar they are to the weights. Notice in the following example that inference is completely ignored in the prediction because the weight associated with it is 0. The most sensitive predictor is WLREC because its weight is 0.2. And the dominant force in the high score is the number of terms, not because the weight is the highest, but because the input combined with the weight is the highest. Yeah, the input of terms is the highest number among those input. Here are a few more points to note for further reference. You can't shuffle weights. They have specific positions they need to be in. Furthermore, both the value of the weight and the value of input determine the overall impact on the final score. Finally, a negative weight will cause some inputs to reduce the final prediction, and vice versa. Multiple inputs, complete runnable code. This code slabs from this example come together in the following code, which creates and executes a narrow network. For clarity, I have written everything out using basic properties of Python, lists, and numbers, but a better way exists that we will begin using in the future. I guess it's NumPy. There's a Python library called NumPy, which stands for Numerical Python. It has very efficient code for creating vectors and performing common functions, such as dot products, without further ado. Here's the same code in NumPy. It's much smaller. As you can say, import NumPy as np, weights equal to np that arrow with a list. Define the narrow network, it's the same. Just use input.weights, and all those lists become an NumPy array, even the input list. So above networks should print out 0.98. Notice that in the NumPy code, you don't have to create a wsum function or weightsum function. Instead, NumPy has a dot function, short for dot product, you can call. Many functions you'll use in the future have NumPy parallels. Making prediction with multiple outputs. What? With multiple outputs? Narrow networks can also make multiple predictions by using only a single input. How it can be? Perhaps a simpler argumentation than multiple inputs is multiple outputs. Prediction occurs the same as if there were 3 disconnected single-weight narrow networks. Okay, by giving the input data, win or loss, you get 3 different outputs. Instead of predicting just whether the team won or lost, you are also predicting whether the players are happy or sad, and the percentage of team members who are hurt. You make this prediction using only the current win or loss record. The weights equal to a list. The narrow network equal to it will take the same argument input and weights, but with different processing code. Here he just used a function element mul. I don't know what it is. The most important comment in this setting is to notice that the 3 predictions are completely separate, unlike narrow networks with multiple inputs and a single output, where the prediction is undeniably connected. This network truly behaves as 3 independent components each receiving the same input data. This makes the network simple to implement. Okay, now I know what this means. When or loss record, which called WLREC. We only get one element from the last or the array as our input. Performing element-wise multiplication. Here's a function element-wise multiplication. We define function of that. We take the input and the weights. The input is number, the weights are vector. The output will be equal to a list with 3 elements. We assert the length of our output equal to the length of weights. For I in the range of that length, we get the output by times the weights with different weights. In this case, it has 3 weights in that thing. It is something like this. We got the same input on every single weight, but with different weights, as you can see. The weights is no longer a whole thing. It's combined by 3 parts or by 3 single different weights. Then we get the predictions result. Predicting with multiple inputs and outputs. Neural networks can predict multiple outputs, giving multiple inputs. Finally, the way you build a network with multiple inputs or outputs can be combined to build a network that has both multiple inputs and multiple outputs. Oh, it's an upgraded version of the previous example. As before, a weight connects each input node to each output node, and prediction occurs in the usual way. Okay, we got multiple inputs and we got multiple outputs. The weights equal to a big list which has 3 little lists. And the neural network, we take the input value and the weights value. We do some processing with the vector multiplication function, inserting one input data point. This dataset is the current status at the beginning of each game for the first 4 games in a session. Okay, it's a thing. Alright, let's have a look at this. For each output performing a weighted sum of inputs. The weight sum is nothing but a dot product. The vector multiple mutations will be equal to this. Okay, what they did is just combine the 1 to many and the many to 1 method together. Multiple inputs and outputs, how does it work? It performs 3 independent weighted sums of the input to make 3 predictions. You can take 2 perspectives on this architecture. Think of it as either 3 weights coming out of each input node, or 3 weights going to each output node. For now, I found the latter to be much more beneficial. Think about this neural network as 3 independent dot products, 3 independent weighted sums of the input. Each output node takes its own weighted sum of the input and makes a prediction. Let's read this again. I'm a little bit confused here. Think about this neural network as 3 independent dot products, 3 independent weighted sums of the input. Each output node takes its own weighted sum of the input and makes a prediction. Oh, so it's something like this. We have to output 3 predictions, and for each prediction we still get the same inputs, but we have to generate different weights. For the hard or not, we generate weights, and for when or not, we generate another weights, and for the set or not, we generate another different weights. So we got basically for this problem, for this network, we will have 3 different weights for the same inputs. This is how I understand it. The WSUM function is made to do the dot product operation for each weight. And for each different weights, we will say here just try to calculate that sum and save it to different output. The output has 3 elements or has another 3 lasts, and for each last we will get different output, right? As mentioned earlier, we are choosing to think about this network as a series of weighted sums. Yeah, actually in this case you get 3 weighted sums. Thus, the previous code creates a new function called VCTMathMul. I hate the Lemming style. I would prefer a more complete stuff. Every word is a complete word. This function iterates through each row of weights. Each row is a vector and makes a prediction using the WSUM function or use a weight_sum function, literally performing 3 consecutive weighted sums and then storing their predictions in a vector called output. A lot more weights are flying around in this one, but it isn't that much more advanced than other networks you've seen. Okay, so this sentence means that every deep learning network, supervised machine learning networks, shares a same structure for doing this. I want to use this list of vectors and a series of weighted sums logic to introduce 2 new concepts. Say the weights variable in step 1 is the list of vectors. A list of vectors is called a matrix. Oh, that's a new idea. A list of vectors is called a matrix. I would say matrix is nothing but list of lists. Sorry. It's as simple as it sounds. Commonly used functions use matrices. One of these is called vector matrix multiplication. The series of weighted sums is exactly that. You take a vector and perform a dot product with every row in a matrix. As you will find out in the next section, NumPy has special functions to help. NumPy is good at matrix operations. Predicting on predictions. Neural networks can be stacked. As the following figures make it clear, you can also take the output of one network and feed it as input to another network. This results in 2 consecutive vector matrix multiplications. It may not yet be clear why you would predict this that way, but some datasets such as image classification contain patterns that are too complex for a single weight matrix. Later, we'll discuss the nature of these patterns. For now, it's sufficient to know this is possible. So as the first step, he just defined two weights. The first layer of weights, the second, which is hidden layers weights, two layer of weight. Then he just defined another function, neural network. It takes the input and weights, and the processing under this function is The hidden layer will be equal to the vector multiple multiplication by taking the input and the weights, the first weights. Then he just did that again by using the hidden layer input or output, whatever you say it, and the weights, the second weights, predicting the hidden layer. Right, it's the same thing. So at the left of our screen, you can see a picture. This picture is the graph representation of the network, of our neural network. And on the right side of our screen, you can see the code. This is the code representation of our neural network. The following listing shows how you can do the same operations coded in the previous section using a convenient Python library called NumPy. Using libraries like NumPy makes your code faster and easier to read and write. The NumPy version, import NumPy as NP. The first weight is a NumPy array. The second weight is also a NumPy array. And we define the neural network. It takes the input and weights. The hidden layer equal to input dot weight, the first weight. The final prediction or the final layer equal to the hidden layer dot the second weights. We call the neural network function, and we get the prediction, the final output. A quick primer on NumPy. Finally, I think I know the meaning of primer now. It's the same as the basic knowledge, or a quick basic introduction on NumPy, something like that. NumPy does a few things for you. Let's reveal the magic. So far in this chapter, we have discussed two new types of mathematical tools, vectors and matrix. You will also learn about different operations that occur on vectors and matrices, including dot product, element-wise multiplication, and addition. The vector matrix multiplication. For these operations, you have written Python functions that can operate on simple Python list objects. In the short term, you will keep writing and using these functions to be sure you fully understand what's going on inside them. But now, I have mentioned NumPy and several of the big operations. I'd like to give you a quick rundown of the basic NumPy use, so you will be ready for the transition to NumPy only chapters. Let's start with the basic again, vectors and matrix. You can create vectors and matrices in multiple ways in NumPy. Most of the common techniques for neural networks are listed in the previous code. Note that the processes for creating a vector and a matrix are identical. If you create a matrix with only one row, you are creating a vector. And as in mathematics in general, you create a matrix by listing rows and columns. I say that only so you can remember the order. Rows come first, columns come second. Okay, let's repeat it again. Rows comes first, column comes second. Okay, I get it. I got it now. I say that, okay, let's say some operations you can perform on these vectors and matrices. Here it is. Import NumPy as NP. You can define the NumPy arrays by giving it a NumPy list. No, by giving it a Python list. And also you can create a ZIL matrix by giving it the rows and the columns. And also read the numbers by using this function. If you say ZILs with the 2 row, 4 column, you'll get something like this. 2 row of ZIL, 4 column of ZIL. And also you can do the multiplication by using this symbol. I don't know how to read this yet, but I know it later. Oh, you can see here the C variable is different. It has 2 rows of values. It's different than A and B. So if you times the C, if you times A and C, it says it performs element-wise multiplication on every row of matrix C, because C has the same number of columns as A. Okay. Go ahead and run all of the previous code. The first bit of at first confusing but eventually heavenly magic should be visible. When you multiply 2 variables with the dot function, NumPy automatically detects what kinds of variables you are working with and tries to figure out the operation you are talking about. This can be convenient, but sometimes makes NumPy code a bit hard to read. Make sure you keep track of each variable type as you go along. The general rule of lump for anything element-wise is that either the 2 variables must have the same number of columns, or one of the variables must have only 1 column. For example, print A times 0.1 multiplies a vector by a single number, 0.1. NumPy says, oh, I bet I'm supposed to do vector scalar multiplication here, and then multiplies the scalar 0.1 by every value in that vector. This looks exactly the same as print C times 0.2, except NumPy knows the C is a matrix. Thus, it performs scalar matrix multiplication, multiplying every element in C by 0.2. Because the scalar has only 1 column, you can multiply it by anything, or divide, or add, or subtract. Next up, print A times B, or multiply B. NumPy first identifies that they are both vectors because neither vector has only 1 column. NumPy checks whether they have an identical number of columns. They do, so NumPy knows to multiply each element by each element based on their positions in the vectors. The same is true with addition, subtraction, and division. Print A times C is perhaps the most elusive. A is a vector with 4 columns, and C is 2 times 4 matrix. Either has only 1 column, so NumPy checks whether they have the same number of columns. They do, so NumPy multiplies the vector A by each row of C, as if it were doing element-wise vector multiplication on each row. Again, the most confusing part is that all of these operations look the same if you don't know which variables are scalars, vectors, or matrices. When you read NumPy, you're really doing 2 things: reading the operations and keeping track of the shape, number of rows, and the columns of each operation. It will take some practice, but eventually it becomes second nature. Let's look at a few examples of matrix multiplication in NumPy. Nothing, the input and output shapes of each matrix. What? Yeah, what he just said is true when you are writing Python code or check others' code. Normally, something that I will always do is to print out every variable shape Only in that way I can understand what's going on in there. It defined two variable a and b. Lampy a equal to lampy.zeros with 1 row 4 column, and b equal to lampy.zeros with 4 rows and 3 columns. Okay, it has different shape, right? They both have different shapes. Say equal to a dot dot with b. What? I couldn't understand what's going on there. There's one golden rule when using the dot function. If you put the row's clones description of the two variables you are dotting next to each other, labeling numbers should always be the same. In this case, you are dot producing 1 row 4 column with 4 rows 3 columns. It works fine and output 1 3 columns. In terms of variable shape, you can think of it as follows, regardless of whether you are dotting vectors or matrices. Their shape, number of rows and columns must line up. The columns of the left matrix must equal to the rows on the right, such as this. AB dot BC will be equal to AC. That's a golden rule. I still couldn't understand what's going on. Let's just run that code to find out what's going on there. First we define the a function. No, we define the a variable lampy.zeros with 2 rows 4 columns. Then we define the b variable with 4 rows and 2 columns. Lampy is not defined, so we have to import lampy as np. No model lambda lampy. That's because we haven't installed it yet, or maybe we just installed but we didn't restart the kernel yet. Okay, maybe we should reopen the chapter notebook. No model lambda lampy, so we have to install it. Let's do this. Pep 3 install lampy. Permission denied because we don't have a sudo permission. So we'll do it here. Requirement already satisfied with that. So what is going on in there? Okay, let's open the chapter notebook with sudo permission. No, we cannot do it. It's quite weird that we cannot import the lampy library. I think I just remove the slap version of chapter notebook. Then install the apt version of that. Then install LAMP. After that, we start that chapter notebook. This time should work. Okay. We just defined the A and B variable here. And we're gonna print out the A variable. And the B variable. It's something like this. What will happen if we use A times B? Operation could not be bursted together with shape of that. It cannot be happening unless we use some function like A dot with B. You know what? Even though I don't know why we will get a shape like this by using the dot product operation. But here's a fun fact. And he just told you that. He just told you that. You know, if the A has a shape of 2, 4, B has a shape of 4, 3, finally you'll get a shape with 2, 3. It's just like a row in here. AB dot BC equal to AC. Even though I don't know how they made that happen. But here's just the row. Fine, let's just forget about it. It's not important if you are using some deep learning or machine learning library like TensorFlow, Keras, and PyTorch or sorts of things. They all have the dot function available for you to use. You don't have to do it by yourself. Summary. To predict, neural networks perform repeated weighted sums of the input. You've seen an increasingly complex variety of neural networks in this chapter. I hope it's clear that a relatively small number of simple rules are used repeatedly to create larger, more advanced neural networks. The network's intelligence it depends on the weight values you give it. Everything we have done in this chapter is a form of what's called forward propagation, wherein a neural network takes input data and makes a prediction. It's called this because you're propagating activation forward through the network, from the input to output. In these examples, activations are all the numbers that are not weight and are unique for every prediction. In the next chapter, you'll learn how to set weights so your neural networks make accurate predictions. Just as prediction is based on several simple techniques that are repeated or stacked on top of each other, weight learning is also a series of simple techniques that are combined many times across an architecture. See you there. So he just introduced you about the linear neural network. You just have to combine different layers together to construct a neural network or model or whatever you call it. We will start to learn the chapter 4 in the next video. So goodbye.